let's go to page 352 and let's do number 575. Okay, it says show that among 4 points, no 3 of which are collinear in a plane, no 3 of which form a right triangle. There exists at least one obtuse triangle. Okay, so this one, what you want to do is you kind of want to use, so 4 points. Imagine if you have 4 points and it form a square. Okay, remember the triangles, any 3 points can make into a triangle, right? So 4 points you can make into 2 triangles in any way. Okay, so the sum of angles in quadratic is 360. So that's without with. So imagine that we try to use that counter example. Okay, let's say there's no obtuse angle, so that means the 4 angles have to be even out, like all 90 degrees. Okay, that's the only way we can. That's the only way we can have no obtuse angles. Okay. Now, but it says no 3 of which form a right angle. So now if you're not allowed to have a right angle, so that means let's say if you decrease this by 1, okay? Let's say if you make this into 89. Well, if you decrease this by 1, that means 1 has to go somewhere, right? Okay. So that means one of these has to become 91, okay? And therefore, no matter what, okay, if you're not allowed to have a right angle, okay, that means you're gonna have at least one obtuse angle. Okay. Okay, so that's it. So again, if you want to write it out, so a square with 4 right angles will have no obtuse angles, okay? But any decrease, since you're not allowed to have a right angle, so you have to decrease it, right? Okay, because you don't want to have obtuse angle. So any decrease in any angle will cause the angle to increase and become obtuse. Okay. And since no right angle since there is no right angle, therefore there must be at least one obtuse angle. Okay, so anyway, that's kind of that. So again, if you just start with the context, you just start with the example and to prove it's unavoidable to have obtuse angle. Okay, if you're not allowed to have right angle. Okay. Let's go to the next one. Okay, if A and B are positive real number, positive numbers, and each of the equation, so you got x squared plus ax plus 2b equal to 0, and you have an x squared plus 2bx plus a equal to 0 have real roots, then what's the smallest value of a plus b? Okay. Okay, so in order to have the positive real roots, that means d had to be greater than or equal to 0. Okay, so that means b squared minus 4ac had to be greater than or equal to 0. And this is from the discriminant. Okay, so let's go and do this. Okay, so b squared minus 4ac had to be greater than or equal to 0. So now, again, don't get confused between this b and this b. Okay, this is the second term coefficient. So in this case, would be the a squared minus 4a c is 2b. Okay, so again, that's your a, b, c of here. So again, don't get confused between this a and this a, this b and this b. Okay, so a squared minus 8b is greater than or equal to 0. Okay, and let's do this side over here. Okay, so same thing. So you got b squared minus 4ac have to be greater than or equal to 0. Okay, so b, so this b is this over here, so be 2b squared minus 4ac greater than or equal to 0. So 4b squared minus 4a is greater than or equal to 0. And okay, divide by 4. Let's go and get rid of the number. So b squared minus a greater than or equal to 0. And let's go and move the a to that side. So b squared is greater than or equal to a. And I'm going to square both sides. So the reason for that, because there's an a squared, so I'm going to square both sides. So b to the 4 greater than or equal to a to the 2. Okay. And I'm going to flip this over. So a squared is less than or equal to b to the 4. Okay, then I'm gonna move this into here. Okay, substitute this into here. Okay, so I got b to the 4. My a squared is kind of less than or equal to b squared. So I'm gonna put this in here. And go and factor out the b. So your critical values. So from here you're gonna get b and b minus 2, and you're going to get b squared plus 2b plus 4 greater than or equal to 0. So your critical value would be 0 and 2. This one you're not going to get a solution. Okay. Okay, so from here you're going to get 0, 2. So inequality, so we kind of have to work through this. Right? Okay, so you want to greater than or equal to 0, so you have this part over here and this part over here. So you're going to get b is less than or equal to 0, or b is greater than or equal to 2. Okay, but remember this has to be positive, right? A and b are positive, so this is no good. Okay. Okay, so we know that b has to be greater than or equal to 2. Okay, now we can go back. Let's go back to here. Okay. So from here we have a squared minus 8b greater than or equal to 0. Move this over. So a squared is greater than or equal to 8b. So a squared greater than or equal to 16. Right? So because of 2. So a, you take the square root, have to be greater than or equal to 4. Okay. Now you don't have to worry about negative, because again both have to be positive, right? Okay, so we have this and this over here. So a plus b, okay, will equal to so when you substitute, since b is greater than or equal to 2, a is greater than or equal to 4, so this would be, so that means you substitute, so a plus b will be greater than or equal to 6, right? Because again, b is greater than or equal to 2, a is greater than or equal to 4. So when you add this together, okay, so you got a, so you got b greater than or equal to 2, b greater than or equal to 4. So when you add, a plus b will greater than or equal to 6. Okay, next one. Okay, 577, so you're giving points. So you got O, A, B, C, and D. And you're going to have a random point over here, P. Okay. Now, so from here to is A, so this is A, and this is B, and so forth and so forth. So I'm going to call this X. Okay, so this X is right over here. Okay. And you're also giving that AP to PD is equal to BP to PC. So you're looking for OP. Okay, so first let's go and write this in a ratio form. So AP to PD means AP over PD equal to BP over PC. Okay, so next is so AP would be equal to, it's going to be equal to, so AP would be equal to the B minus the A. So B minus the A will give you these, then you have to plus the X. Okay, now PD, this over here, okay, this would be equal to the D, okay, minus the B, okay, minus the B, right? So this is B, this is D, so D minus the B will give you this over here, okay, and then you have to minus the X to give you the PD. So again, so this is the D minus the B minus the X, give you the PD. Okay, now the BP would be just the X. The PC, this part over here, will equal to the C minus the B minus the X. Okay. Okay, so once we get these, now rest of it just algebra. So just go and work it out. Okay, so first I'm going to do is I'm going to cross multiply. Okay, so B minus A plus X times C minus B minus X equal to X times D minus B minus X. Okay, and next is I need to do the factoring. So I'm going to kind of group things a little bit so it's easier to see. Okay, so I'm going to make this into B minus A plus X, and this one I'm going to make into C minus B minus X. Okay, so basically I'm group this into group, and this will give me equal to X times D minus B minus X. And next is I'm going to go ahead and multiply. Okay, so now multiply, I don't multiply every single detail, so I'm going to just use a FOIL method. Think of this as a term. So the first term would be B minus A times C minus B. So F O I and L. Okay. And this will equal to, same thing over here, would be X D minus B minus X squared. Okay, so now the minus X squared will cancel out. So this will cancel out. And next, I'm going to try to group things. So all these have x, so I'm going to move everything to here. Okay, so I got b minus a times c minus b equal to x times d minus b. So move this over, becomes plus x times b minus a, and this one will be minus x c minus b. Okay, next I'm going to factor the x. So I get d minus b from here. Okay, let's just do this. Okay, so I factor the x, and then after that I can go and divide. So I'm solving for x. So divide this whole thing. So x equal to b minus a, c minus b, over this bracket over here, so d minus b plus b minus a minus c minus b. Okay, so now just have to work everything out. So x equal to, use your FOIL method, so it'd be bc minus b squared, so use FOIL method, minus ac plus ab. On the bottom, I get d minus b plus b minus a minus c plus b. Okay. And then I have the minus b plus b will cancel out. Okay. And I'm going to arrange this in order, so I get negative a plus b minus c plus d. On the top, I get bc minus b squared minus ac plus ab. Okay, so continue. So x is equal to, and I'm going to multiply by -1 on everything and arrange the terms. So x equal to a minus b plus c minus d. I don't like the negative beginning. So everything got changed sign. And I'm going to put this in the front. So this is ac, okay? And minus ab. Right? Again, everything got changed sign, right? And then minus bc plus b squared. Okay, so that's what we have. Okay, so once we got x, okay? So to find OP, so OP equal to B plus X, right? Equal to B plus X, that's OP. Okay, so go and add. So OP equal to, it's not again to common denominator now, okay? So B, I have to have all this, right? So I get AB minus B squared plus BC minus BD. Okay, so this whole thing is a B, right? Again, I'm making to common denominator. And then you have to plus that, so plus AC minus AB minus BC plus B squared. Okay, so now we have the AB minus AB can cancel out. And I have minus B squared plus B squared can cancel out. And I have a plus BC minus BC can cancel out. So OP actually come up pretty nice. So you got AC minus BD over A minus B plus C minus D. Okay, so it's pretty messy, but it's just a basic algebra of move things around. Okay, let's go to the next one. Okay, suppose we're giving, okay, so a figure, a configuration made of congruent regular hexagons, where each hexagon share a side with another hexagon. What is the largest k such that the figure cannot have a k vertices. And it can kind of give you an example. Okay. So so if you look at the number, so the number that you cannot, okay. So we know that 1 you cannot, right? Because as hexagon, the minimum vertex, okay, is 6. So 2 you cannot, 3 cannot, 4 cannot, 5 cannot. For 6, you're going to get this configuration. Okay. And 7, again, you cannot. Okay. 8 cannot. 9, again, cannot. Now, once you get 10, you can. Okay. So the 10. See, when you have this kind of configuration, so one hexagon will give you 6. The next hexagon, when you have this kind of configuration, will give you 10, so it will be plus 4. And if you have this kind of configuration, if you line it up, it keep adding 4. So this will give you 14. Okay. Now, if you have a different way of doing this is if you have it this way. So in this case, you're going to get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this one is going to, so if you have 1, you're going to get 6. 2, you're going to get 10, and after you get 13. Okay, and each additional one. So when you class it like that, each additional one you're going to get plus 3. So first one you get. So when you have 2, you're going to get plus 4, but after that you get plus 3 after that. Okay, so this one you're going to get 2. When you get 2 hexagons like this, so this one is good. Okay. Now when you get to 11, again 11 you cannot. Okay, 12 cannot. So 13 we can have, right? 13 is over here. So when you cross the 3 like that, you get 13. So you can have. Okay. 14 if you got 3 in line together, you get 14. So 14 is good. Okay. 15 is impossible. Okay. And 16 is this one here. Okay. So this one is good. So after that, you can do any one of them. So 17, again, you start. Notice you start with 10. Your 10 is your base number. And after you can have combination of plus 3 or plus 4. Okay. So 17, you can have 10 plus 3 plus 4. Okay. So you can have. So 18, you can have 10 plus 4 plus 4. Okay. 19, you can have 10 plus 3 plus 3 plus 3. So anything after that you can get. Okay. Any combination. So the largest number that you cannot is the 15. Okay, so 15 is the largest number that's impossible. Anything after that you can get. Okay, because again from here you can have 10 plus 3 plus 3. Right. Okay, again this when you have straight configuration you plus 4. When you have cluster configuration you plus 3. So anything up to 10, okay, you can either plus 3 or plus 4. So any combination up to that you can have. So the largest number that is impossible is 15, and so 15 would be the answer. Okay, we're going to skip number 579, so let's go to 580. Show that if R1 and R2 are the distinct real roots of, you got x squared plus px plus 8 equal to 0. You want to show that R1 absolutely of R1 plus R2 is greater than 4 square root of 2. Okay, so from your root equation, you got x squared minus R1 plus R2, x plus R1, R2 equal to 0. So by doing, and again, both are real roots. So that means D have to be greater than 0, and R1, R2 equal to 8. Okay, so this equal to that. And D is, again, both are real roots. So D have to be greater than 0, right? And D equal to B squared minus 4AC. So substitute this into here. So you got B squared minus 4AC is greater than 0. Okay, and so B is the P. So you get P squared minus 4. A is 1. C is 8. Okay. So P squared minus 32 is greater than 0. So P squared is greater than 32. And take the square root, so P has to be greater than 4 square root of 2. Okay. And from here, right, again, because, and the P So if you notice that P is your, if you match it up, because again we deal with absolute value, so P would be just the absolute value of R1 plus R2, right? Again, because you can just match up. See, P is negative R1 plus R2, but because we're taking absolute value, so P would be just the R1, R2. Okay, so this will equal to that. So therefore, it has to be greater than 4 square root of 2, and that's your proof. Okay. Okay, let's go to the next one. Okay, it says if the decimal part of x is equal to x minus the floor function of x, show that the all real number x and y that the decimal function of x plus y is equal to x. IFF means if, only if y is integer. Okay. So what we do is we apply the definition in here. So whatever is here would be have this kind of function. So if you have x plus y, so anytime when you see x, it becomes xy. So it be x plus y, right? X become x plus y minus x plus y function, right? And this over here, so y is equal to y minus the floor function of y, right? So if you then what you do is okay. Oh, we can substitute. So x from okay, let's see. So next step is this is going to be equal to x minus. Remember, we want to show that this is equal to that, right? So we want to say that if this is equal to that, then y must be an integer. So we're going to set this equal to that. So this is equal to x minus the floor function of that, right? So again, this is equal to that. So again, we want to show that when this is equal to that, y must be an integer. So this equal to that. So that's where this came from. Okay, so the x will cancel out. Okay, so I have the, and I'm going to move this over. So y equal to this plus that minus this. Okay. Okay, but notice that this is the integer. Remember, this is going to be the floor function, right? So this is the integer, right? And this is the integer. So when so y equal to integer minus integer. So therefore, y must be integer. So again, when this equal to that, then y must be integer. Again, this came from here, okay? Because again, when the problem says when this equal to that, so when this equal to that, right? Then y must be integer. You can see that, right? Because this is the integer, this is the integer, so y must be an integer.